Okay, so before coming to the end of before coming to the end of differentiation, we're first gonna talk about how to find maximum and minimum of a function using calculus. So if we draw a function, let's say we draw a function like that, right? This is clearly the minimum of a function, and this is the maximum of a function. How do I calculate? How do I obtain the numerical numbers describing the function's minimum and maximum? You can use calculus to do so. And the observation is that at the minimum and maximum, right, the gradient of the tangent line is 0 because the tangent line is horizontal. So the gradient is for both minimum and maximum points is 0. So yeah, so that's for minimum and maximum. But the question now is how do I distinguish between minimum and maximum points? Right? If I have a function, let's say f of x equals to x squared, and I take the derivative, which gives me 2x, right? The 0, if I set derivative is equal to 0, you can see that this gives me a stationary point, right? A stationary point where if I move left and right, the function doesn't change by a lot, and it gives me a stationary point at x equals to 0. From the graph, we know that y equals to x squared has a minimum point, but if I take the derivative, we see that both minimum point and maximum points give me gradient of 0. So how do I know whether this is min or maximum? And the answer is to actually take a derivative again. So how this works is that if we take a look at this example graph over here above, right, you see that if I plot the gradient of this function with respect to x, right? So I'm plotting the derivative. So let me just label it clearly. This is the function f of x, right? Then I'm gonna plot the derivative. I'm gonna plot the derivative f prime of x. So f prime of x, and it's gonna look something like that. So let's say this is y equals 0. So this line is the y equals to 0 line. You can see that here the derivative is negative, right? At this point the derivative is negative, so it's gonna start off negative. Then when we hit this point, the derivative over here is negative, and it's slowly increasing, right? Becoming less and less negative. And at the minimum point is 0. Then the gradient over here is increasing again. The tangent is getting steeper and steeper until around here the tangent gets kind of to a maximum before it starts decreasing to 0 again. So it's gonna look something like that. And over here the gradient is 0 again, and so on. So this red graph is the plot of the derivative f prime of x. So can we notice the difference between a maximum and a minimum? You see that when we're at a minimum, right, the left and right is higher than it, right? And then we see that if we look at the f prime of x, the red graph, we see that it starts off from a negative value, or rather, yeah, it starts off from a negative value, and then it becomes a positive value. Right? It starts from negative and becomes positive. Whereas for the maximum over here, where it's a frowning face, right? The gradient is initially positive, right? Over here is positive, and then after the maximum point, the gradient becomes negative. In other words, right, near the minimum and maximum points, you can see that the derivative function itself is either increasing or decreasing respectively. For if the if the derivative function itself is increasing, then that indicates its minimum point. Whereas if the derivative function is decreasing, that indicates that it's a maximum point. So how do I know whether the derivative function is increasing or decreasing, right? Increasing or decreasing is, in other words, right, I want to find, in order to find whether a function is increasing or decreasing at a particular point, I need to take its derivative again, right? So I need to take its derivative, so I'm taking the derivative of this f prime of x. So in other words, right, in order to find whether, to determine if a function, if a point is maximum or minimum, I take the second derivative. So I take d over dx of d over dx of f. And usually we denote this as d2 over dx squared f. Right, okay. So this symbol over here represents the second derivative of f. Sometimes we also write it as f prime prime of x, but I personally prefer this notation. So you see that, so if the second derivative is positive, right? Second derivative is positive, meaning that the derivative is increasing, then it's a minimum point. So if the second derivative is increasing, if the second derivative is positive, then it's a minimum point, because that implies that the derivative is increasing. Whereas if the second derivative is negative, that implies that the derivative is decreasing, which corresponds to this point over here. I see that the derivative function is decreasing over here. So that's how, in order to determine whether a point is minimum or maximum, we take the second derivative. Now, if it's positive, great, it's minimum. If it's negative, it's a maximum. What if it's precisely 0? And it turns out actually we do not have enough information to conclude whether it's a maximum or minimum. So an example of a function that has a second derivative equal to 0 would be x to the 4, right? If we plot x to the 4, it actually looks something like that. So actually x equals to 0 is a minimum point, but we take the second derivative, we're going to get derivative of 4x cubed, and that's going to be 12x squared. So at x equals to 0, right? At x equals to 0, this one, 12x squared, is still 0. So the second derivative is 0 is not enough information to conclude whether it's a minimum or maximum point. So often in physics, we'll use calculus to find the minimum points or the maximum points of a function. And a very straightforward example is example that we'll see very soon is how to maximize the range of a cannonball, of a projectile, or a parabola, right? So basically what we're going to end up getting is that we're going to get a range, which let's say denote r. We're going to get a range as a function of theta. So as we vary theta, right, as we vary this angle, whether it's steep, whether it's very shallow or very steep, right, as we vary the angle theta, we're going to get a different value for the range. And we're going to maximize the range with respect to all our thetas, right, all the choices of thetas. So if we plot this, it's going to give us some graph. And we're going to maximize the range. So we're going to actually need to differentiate the range with respect to theta. So so that's an example which we'll soon see very soon, and when we talk about projectile motion. So that concludes finding minimum and maximum for functions using calculus, using differentiation. So next up, we're going to talk about integration and what it means.